Hi, welcome to Ordinary Differential Equations. Today's topic is going to be about direction field. Direction field is a graphical way of analyzing differential equations. For most of the semester, we are going to concentrate on algebraic or calculus style of approaching differential equation. This is a graphical style that gives us qualitative ideas about the solution but does not provide uh, the type of solutions that we see for most of the semester. First, what is meant by a field? Well, uh, think about a cornfield. Cornfield, you see a corn stalk at every point in the field, and when the wind blows, each of them is pointing in a different direction, perhaps, and that is a good idea for what a field is. Most applications in engineering or in physics make use of a so-called vector field. Vector field means that you have a vector at each point of space. And as you go around in space, these vectors could be different. So I'm going to go ahead and draw or show you some pictures of various type of vector fields. What are we going to do? We are going to look at a special kind of fields called direction field or slope field. It's a little bit simpler than a vector field, and that's what we are going to be using. We are going to look at differential equations that we started the semester with. We are going to call the right-hand side slope function or rate function. Here's an example of a simple one. Y prime is equal to minus x plus y. We are going to analyze this with the concept of a direction field, especially paying attention to if we can tell if the derivative, if the function is increasing or decreasing. Then we come to the so-called autonomous differential equations. These are differential equations where the right-hand side, the independent variable does not show up. So this x that you see here is missing from this one. We are going to study critical points, so-called equilibrium solutions or stationary solutions. And take a look at a famous example called logistic equation in this context. Learn that during the analysis we are going to have something called a phase line, and certain type of solutions are going to be characterized as stable or unstable and so on. Okay, so going back, we said the field, simplest idea is like a cornfield. Vector field, let's go ahead, let me show you some examples of vector field. So on your Blackboard, you have access to this page. I'll just explain some aspects of it today, and the software will be delegated to another day. So example number one is the velocity field in a hurricane. So if I have a hurricane, this happens to be, I guess, Sandy when it was approaching New York City. You see that at every point an arrow is drawn. So it's a velocity field, and the velocity shows how fast the wind is blowing and in which direction. This is something you need to know when a hurricane approaches to know how bad the situation is going to be. So as you come close to the eye of the hurricane, the vectors get bigger. As you go far away, vectors are smaller, and lots of other information is packed into this. So that was one example. The next example is gravitational field of say a bunch of planets and so on. So if you're looking at the Earth and the Moon, and you have some satellite somewhere, some mass somewhere in space, there's going to be a force exerted on this. So consider a kilogram, mass of a kilogram in space. It's going to be pulled in a certain direction. That vector that shows the direction of the force on this mass, that's going to be the gravitational field at that point. If you come closer to the moon, of course, it's point toward the moon. If you come closer to the Earth, it's going to point toward the Earth. and some complicated pattern is going to exist in space. So that's going to be a gravitational field. We said a field is a collection of vectors that fills up space, and they are drawn based on certain physical laws. So let's go ahead and take a look at some other examples quickly. Another place that you see fields is in electromagnetism. So if you have one charge or two bunch of charges, they have an electric field associated with them, which means if you have a charge of +1 somewhere in space, what would be the force on that charge? That's going to define the electric field of a charge in space. So in this, on the right hand side, we have a positive and negative charge, and you see that the electric field here is much more complicated. Then you'll learn more about that in your electromagnetism class. Magnetic field, probably played with something like that in high school or elementary school even. So you might have a magnet, and if you put a compass around this magnet, each compass at each point is going to line itself with the magnetic field of that point. And of course, if you pour something like iron shaving or something on a piece of paper and shake it up, they're all going to line themselves up with the magnetic field, and you see some peculiar pattern. The last example here I have to show you is something very peculiar looking. Presumably the pole of Saturn. You see some sort of a vortex field. Perhaps some of you get interested and go investigate that. So these are ideas of vector fields that you're going to see in your variety of engineering classes. Ours is a step simpler. We have just a number at each point of space as opposed to having a vector. So 1 degree simpler. We call this thing a direction field, or call it a slope field, and it is used in analyzing differential equation. The right hand side equation are either called slope function or rate function. Let's go ahead analyze a rather simple case. Let's say I have a differential equation y prime is equal to minus x plus y. This is particularly simple. Coming lectures we are going to learn how to actually solve this thing. But as a word of warning, generally differential equations cannot be solved with the neat methods that we approach them in this course. Rather, most often they are so complicated we have to resort to a graphical way or approximate way of solving it, and all of those are based on the concept of direction field. But let's start with a simple one so that we don't get into deep waters right away. So y prime is equal to minus x plus y. We want to draw the direction field for this thing, and for example find out where is the function, the solution will be increasing, where would it be decreasing. So here's my example. So I have y prime is equal to, say, minus x plus y. So y prime means, of course, that's the derivative of y with respect to x. What we want to do is to draw direction field for this differential equation. What does that mean? Well, direction field always happening in our coordinate system. So say we have x and y, or whatever the pair of variables happen to be. So let's see, what does y prime represent? You remember from calculus that if you have y as a function of x, so if y as a function of x was some sort of a curve like that, then y prime would have represented the slope of the tangent line. So y prime, you remember, this is a slope of tangent line. So when we write a differential equation, we are specifying slope of a tangent line to a certain function. It's just that we don't know what the function is. The holy grail of this whole thing is to figure out what the function was that gave that particular slope. How do we specify the slope? At any given point in the page, we tell you what the slope is. So for example, like what? Let's choose a particular point. Let's suppose I take x equal to 1 and y equal to 2. So here's a point 1 and 2. Okay, how does my differential equation say anything? The differential equation says take x and y of your point, calculate minus x plus y. So I'll have minus 1 plus 2. That is supposed to be my slope at that time, at that point. Y prime is this. So y prime is equal to 1. Well, you remember from your calculus and such, perhaps you showed it by y prime. Sometimes they use the letter m for the slope. So what is meant here is that whatever that function is at this point as a slope 1. Well, what does a slope 1 look like? Slope 1 looks like a line that starts going at about 45 degrees. So at this point, slope is 1. Slope of this is 1. The location was 1 and 2, and the slope is 1. Well, the function we know perhaps one point of it, slope of it, but how about the rest of it? So let's go ahead. We send a trial balloon, essentially. We send a trial balloon to every point of the page and calculate the slope at that point and draw a little line segment according to that slope. So these line segments has to remind you of that idea of field or the cornstalk or vector field, something like that. But here the intention is that you're just representing the slope. So let's try, just for good measure, let's try another point. Say suppose I am at point say 1.5, and then I come at point, for example, perhaps 3. So I'm at the point 1.5 and 3. 1.5 and 3. So what would my y prime in this case? So y prime is going to be my x, which is minus 1.5, plus y, which is, well, 3. And when I add them, I get 1.5. So what does that mean? Well, it's a slope of a certain function that passes through that point. Slope of it is 1.5. So a little bit steeper angle than this one was, so we draw a little line segment there where the slope is 1.5. Well, how about some other points? Just go ahead and experiment with a variety of points. So for example, suppose here I take the point 2 and let me use the color 2 and 0. So x is 2, y is 0. What's going to happen there? Y prime, x is 2, so minus 2, and y is 0. And this whole thing becomes minus 2. So at this point, my slope is minus 2, and I am now going, I am going with slope minus 2, which means going down, and the slope of a tangent line to some function is that. So suppose we take another point, in this case minus 2 and minus 1. So what would be the y prime for this point? Y prime is going to be x is minus 2. X is 2, we are subtracting the x, minus x plus y. Y itself is minus 1, so the total is minus 3. and the slope of -3 means I'm going down even the faster slope than the previous one. Well, you notice that we jumped around, chose a certain bunch of points, and drew a little line segment at each of them. So the idea comes up on where does this stop? How many of these line segments do we draw? What do we expect to get out of this? Well, in effect, you have to think about doing this thing for every point of the page. So that means infinitely many points. Of course, that is not practical. So what do people do instead of attempting infinitely many line segments or tangent lines to be drawn? The standard approach is the following. Put a grid. The grid size depends on your patience or your budget and so on. So put a grid, and each point of this grid draw that little line. So at each point of the grid, you go ahead and calculate the x, y of that point, plug it in whatever formula you might be having. So in our case was a simple minus x plus y, but whatever you have here, you plug it in that. Then at each point you draw a little line segment representing the tangent line to your solution. So if you have many of these, then you form a so-called direction field. And by looking at that, you can get a sense of how the solution is going to behave. So you essentially have to follow your nose. So you start at a certain point, which is going to be the initial point of your the solution that you want, and you want to know, well, in which direction you are going to be traveling. And a certain point later on, you want to continue that by following the next direction line that you have, and perhaps the next direction line, and get a sense as to overall direction of your solution. So you're trying to envision a function that as it is laid out on this page, it's going to be tangent to the directions that you have drawn. So you get a sense of which way the function is going to travel. So how do we use this thing for analysis? Okay, the steps that we are going to use is that let's take this one, y prime is equal to minus x plus y, and what kind of information can we extract from our direction field? For example, if I have this, I say consider y prime is equal to minus x plus y. We can answer the following question: when is y an increasing function? Notice we don't have the solution yet. We don't know what y is, but we can say certain things about that solution, that missing solution, before we even have the solution. That's the advantage of the direction field. I'll say increasing function means, well, from calculus we know increasing means y prime is positive. Increasing means y prime is positive. Well, this is my y prime, so minus x plus y is positive. Well, we know a little bit about inequalities. We can rewrite this thing as y is larger than x. So if y is larger than x, our solution will be increasing. Now, what is y larger than x? We go ahead, well, what is y less than x? What's y larger than x? break even will be when y is equal to x. So y equal to x is of course our famous 45-degree line. So y equal to x, here's my y is equal to x. Up here is when y is larger than x, and down here is where y is less than x. So what does this mean? It means that if I am on this side of this line, if I start anywhere on this side, minus x plus y will be positive, and at that point I'll be pulling up, I'll be increasing. So at that point your function will be going up. Down here, minus x plus y will be negative. Therefore, y prime will be negative. Therefore, my function will be decreasing. So I'll have increasing here and decreasing here. Okay, so we could tell a little bit about the solution depending on where we are on the page. We know where the function is increasing, the solution is increasing, where it is decreasing. How about right in between, right there, when y and x are equal? Of course, y prime is 0. Y prime 0, what does that mean? It means the function is flat at that point. So on the left it goes up, right on the line is flat, on the right side it is pointing downward. Okay, now we realize the complication of the amount of work that needs to be done here, and the idea that you draw a direction field at every point of a grid. That sounds like a daunting task, and you don't have to hide it. Yes, it is a daunting task. We try to simplify that in the future, but right now let's go look at problems that we can do easily, and perhaps they are a little bit more manageable. This type of equations that we are going to look at that are a bit more manageable are called autonomous differential equations. Autonomous differential equations, on the right hand side we just have our dependent variable. The independent variable does not show up. Let me write a simple example. Like if I write y prime is equal to 2y, notice there is no x's on the right hand side, no x's or t's or whatever. It's just the same letter that you had, the same variable you had on this side. It's called autonomous. Autonomous differential equations are an important class of differential equations. They are going to show up in your science classes as well. It simply means the time itself is not influencing the system, or the time has been averaged out in your system. Perhaps you're looking at a certain process in a more coarser way than looking at cyclical details. Okay, either simplified or truly speaking autonomous. We are going to take a look at these equations. Well, you remember here we mentioned that to differentiate between increasing and decreasing, we set the right hand side equal to 0, and that is going to tell us the distinction between increasing and decreasing. Same thing happens for autonomous differential equation. Autonomous differential equations, let's take a simple example of it and work that out. So I will let's write autonomous differential equations. Here's an example. So autonomous differential equation, the independent variable that's either your x, or typically is x or t, does not show explicitly. What's an example of it? Y prime is equal to, let me make up some example. So 6 minus 2 y times y. This example falls in the category of important problems we are going to look at extensively, sometimes referred to as logistic equation, something that's used in population studies in biology and similar sciences. Okay, suppose we want to decide where is it that the y is positive and where is it that the y is negative. Well, in between these two cases, we will be encountering where where y prime is positive, where y prime is negative, and in between these two cases where y prime is 0. So this meant your solution is increasing, this meant the solution is decreasing, and now y prime equal to 0, we are going to call it equilibrium or stationary. The situations where this happens, we call it equilibrium or stationary. That's a terminology that is used in differential equations. Well, let's take this thing. Easiest thing is to actually set it equal to 0. There's a simple equation. Either the first factor is 0 or the second factor is 0. This one just tells us y is equal to 3. Well, this one there's nothing to do, so y equal to 0. And these two numbers are called critical values, critical solutions, critical values, or critical solutions. What does it mean? What is so critical about it? Well, suppose you solve your equation starting at exactly this critical value. What happens? Well, of course, if I put y equal to 3 here, I get 0. 6 minus 2 times 3 is 0. Times 3 is still 0. Y prime is 0. What does it mean when a derivative is 0? It means that function is not changing. Is that right? So if I have in my plane at some x and y is equal to 3. So whatever for x and the y is equal to 3. If I start at such a point, my derivative is 0, and derivative being 0 is just like we mentioned here. 0 derivative, well, it means you are flat, you're moving in a flat direction. Well, suppose I do move in a flat direction, horizontal direction. Whatever point I go at still has a y coordinate equal to 3, and I take it and plug it back here, and that arrow still continuing horizontally and then continuing and continuing how far you go, you are always on this horizontal line, which is y equal to 3. And y equal to 3 is a solution of this differential equation. It's very easy. Y equal to 3, a function that is always just equal to 3 is a solution, because if I put this thing here, I get 0. And if I take a derivative of this, I get 0. So of course, the 0 is equal to 0. And I have a solution. So this is a solution. Given that it's always constant, it's called a steady state solution, steady solution, or sometimes called the critical solution. Is there another critical solution? Yes. The other one is just y equal to 0. So I have another critical solution. Let's color it in red. So this is y equal to 0. So this differential equation has two steady solutions. One is y equal to 0 and the other one is y equal to 3. So if I'm on this line, I'm forever stuck at that line. If I am this on the yellow line, I'm forever stuck at the yellow line. Well, what if I start somewhere in between the yellow and the red? Suppose I start at this point. Anywhere in this strip is fair game to consider. So I'm looking at this point of what is y of it. Let's say y is equal to 1. If y is equal to 1, when I put it here, what do I get? 1 times 6 minus 2, that's 4. That means the slope of my solution is 4, and that means I'm going to be traveling upward here. Okay, slope is 4, which means from left to right I'll be going up. Well, if I try any point between these two lines, I'll get a positive slope. Okay, if I am very close to the red line, that means my y is very close to 0. If I put it here, I get a number that's close to 0, but it's positive. All right, y is positive. 6 minus 2 times a small number is a positive number. Product of two positives is positive. Y prime becomes positive. So if I am down here, I have a small slope, but it's positive. As I go up, my slope gradually increases, then increases again. At some point, in this case at the midpoint, slope reaches the maximum it can be, and after that, as I approach the line 3, my slope starts to decrease again. Why is that? Because when y comes close to 3, 6 minus 2 times the number that's close to 3 is going to be close to 0, times y is still close to 0, and my slope is small. So as I go up, my slope becomes less and less, and by the time I come close to this yellow line, I become almost flat. So if I start at some point in between the yellow and the red, I pull myself up all the way to the yellow. Well, what if I start at above both of these lines? So what if I start at some point up here? Say my y is 5. Well, 6 minus 2 times 5, that's going to be 6 minus 10. It's going to be minus 4 times 5 is going to be minus 20. So my slope is a negative number. A negative slope, we learn a negative slope means coming downward. As I come downward, I plug my y here. So long as y is larger than 3, this factor is negative, and I'm always going to be descending. As I descend and I come close to 3, this factor becomes close to 0, and that means I'm going to flatten out. So as I come down, my one factor is going to be close to 0, and I'll be flattening out like this. In this solution, these lines never crisscross each other. Almost all cases, they stay away from each other. In some exceptional cases, they can become tangent, but we almost never see those cases. So these lines, these curves that you draw, all of them stay away from all the other ones. This is, imagine an airplane trying to reach the cruising altitude but never reaching it. This one, think about an airplane that is coming down toward the runway, but it's never making the touchdown, it just comes closer and closer. Well, what if we were in this neighborhood? What if I was here? That is, y was a negative number. If y is a negative number, 6 minus 2y is a positive number, but y is negative, so the product of the two of them becomes negative. And that means if I'm below, I am going down. As I go down, my y increases. I go down even faster and faster, and that's what happens. What if we back our way up? As we back our way up, where y is negative but a small number, when y is a small number, this whole thing becomes very small, and that means we are almost flat. Okay, so close to all equilibrium solutions, we are almost flat. Okay, what now? If we start some other places in the plane and draw the curve, all we are going to get is exactly what we had, except that the solution is translated to the right or left. So the next one is going to be just like what we drew, and the next one you draw from here is going to be just like that one. And if you go here and draw another solution, it's going to just look like this. So you can draw as many of these as you want, and each of them is just a copy of the other one, and that's what we refer to as translation property. This translation property for autonomous equations is that once you have one of the solutions, you can just move it left and right, and you get all the other members of the family. They all look like this. Okay, next, remember we said we are going to talk about qualitative aspect of a solution. Throughout all of this, I'm not giving you what is the equation of this curve or formula or anything like that. We are just getting some very general pictures out of here. One of the important things that we are going to discuss several times in the course is the issue of stability. What does it mean for something to be stable or unstable? Okay, for example, if you take a chair and move it on two of its legs, most often it comes back to what it was. Of course, if you move it too far out, then the chair is actually going to fall. An idea similar to that happens in mathematics as well. So if I have this yellow solution here, if I go a little bit above or below it and track the solution that passed through this location, I see that my solution comes back to the yellow point. If yellow line, if I'm down here and I track this solution, that also comes close to that yellow equilibrium solution. For that reason, this is referred to as a stable equilibrium. So stability means if you take something and move it slightly from its equilibrium position, it comes back to the equilibrium position. That's called stable. How about the red one? Red one, if I move a little bit away from the red one, if I go up here or down here, the solution just escapes, goes somewhere else. If I am below it, the solution also escapes. For this reason, this is called unstable. So unstable equilibrium solution is an equilibrium solution that if you move slightly away from it, and then you move for good and never come back. Some rare cases, we have a mixture of stable and unstable. You might see it every now and then, that you might have a line, and perhaps on one side of it you come close to it, and on the other side you run away from it. You're going to see it in some of the problems. So that's called semi-stable. Semi-stable, we are going to see later on where it comes up. So let's go ahead and summarize our discoveries in the context of this equation. We said an equation is called logistic equation. The person who introduced it was just looking for a word that will rhyme with logarithmic and arithmetic, so it called it logistic. It meant something in mathematics. There has no connotation of military or management or anything like that. It's just called a logistic equation, which is it's just a name. So logistic equation looks like this. It's used in population studies quite a bit, so that's why the letter P is used in many textbooks to refer to this. So P is a population of something, such as a number of fish in a pond or something like that. A and B has something to do with some numbers related to the species that you're considering, then the environment that you're looking at. And in this context, so let's go ahead and take a look at another example of a logistic equation. See how can we summarize all of these things and answer things quickly. So suppose I have y prime is equal to 5 minus 3y times y. So I want to find critical solutions, and I want to label them as stable versus unstable. Well, we set the right hand side equal to 0. We find the roots of it. Y is equal to 0 and y. We set this one equal to 0. I'll guess 5/3. It is customary to draw a line, in this case a vertical line because our y-axis was like vertical, and pinpoint the two solutions that you have, 0 and the other one will be 5/3. So the critical solutions, so these are the critical solutions. And then do a little bit of number checking or sign analysis or something like that. If I have a number larger than 5/3, so if I number larger than 5/3, I multiply it by 3, so I'm larger than 5, I subtract from 5, so it's going to be negative. So if y is larger than 5/3, y prime is negative, and I am decreasing. If y is slightly below 5/3 and I put it here, I get something positive. So it means I am increasing. So if I go above it, I come back down. If I go below it, I go back up. So for that reason, this is going to be called stable. How about situation near 0? 0, if you go a little bit above it, y is a small positive number, you put it here, you get positive number. Positive means y is increasing. Increasing means you're escaping away. Well, what if y had started with a small negative number? Well, this is positive, this is negative, y prime becomes negative, and now I am moving away from 0. So for that reason, it's going to be called unstable. This is unstable point. The line itself, this line that we draw with this game that we're playing on it, this is called the phase line. Phase line is a small part of something much bigger we might look at later on, phase plane, but this is just a phase line for the equation that we had. So let's go back. What did we learn? We have something called the direction field. That is, at every point of the page, we have a number that is given by whatever we have on the right-hand side. That is the slope of the tangent line to a graph of the function that we are searching. There are many functions who are solution of this depending on your, depending on the initial point, we get a different member of the so-called family. We said it's easy to check to see where the solution is going to be increasing and where it is decreasing. the expression on the right hand side. We set it, we make an inequality and find out where it is positive and negative, and that's going to tell us that. So drawing the direction field requires a bit of a patience. So we do our best, perhaps make a 5 by 5 grid, and then we have to deal with like maybe 25 numbers to be found, but still it's going to be a bit more taxing than exercises that we have done before. So there is a class of differential equations called autonomous differential equations. They are missing the independent variable in them. Simplest example would be, say, y prime is equal to 2y. There's no x's here. That makes it autonomous. We had equilibrium solution, which are simply solutions of this right-hand side is equal to 0. It's also called stationary. One of the most important examples in this regard is a so-called logistic equation. It's like a quadratic on the right-hand side. To analyze it, we use the phase line. We labeled solutions as stable or unstable, and we also said all autonomous differential equations have translation property. Once you get one member of the family of solutions, as you translate it to left or right, all of them are also solutions. Okay, you want to read the text and try several examples in this case, and then we'll have much more to say about this later on. Until later, good luck and God bless.